Hello everyone, my name is Chirag Anand and today I am going to describe you about my project which I have done on compilers. So basically when you execute a C code, first the C code will get converted into assembly language instructions, and then these assembly language instructions will get converted into an intermediate level code. Then we execute the intermediate level code. I have explained these functionalities through three different modules, and they are: the first module is C to assembly. So here I take the input file, which is a C file, and I convert the C instructions into the assembly language instructions. This is a sample C file. Here the syntax is defined by my own. Like, to declare a variable, you have the data type and followed by the variable name. To read a value into a variable, I have the scanf and followed by the variable name. And then also it allows the expressions. The value of this expression can be evaluated and stored into another variable. So let me walk you through the code. First, I'm reading each line from the C file and I'm passing it to the function write to ASM. Here I'm checking if the operation is int or scanf or printf, and I'm writing the assembly level instructions accordingly into the .asm file which is to be generated. And then if I encounter an expression such as a is equals to b plus c or c is equals to d plus 10, I pass the value, that whole expression, to the function equate and write. Here equate and write will evaluate the expression based on an expression evaluator written by me. I'll explain you, or I'll show you the structure which I've used for expression evaluator. It is a stack. So it consists of a node which consists of data and type. The data could be a variable or a number. So if type is 1, it signifies it is a variable, and if type is 0, it signifies it is a number. Now moving to the expression evaluation, I'll explain you that with an example. So here let us consider the first example: a is equals to b plus c plus d. So what happens over here is, first the b plus c value will get evaluated, and then the value of this b plus c will get added to the value d. As the precedence levels of both the operators is same, which is the addition, so it moves from left to right. There is no complexity in this. Let's move to another example where the precedence level of multiplication is more than addition. So the value that gets evaluated first is c into d, and then this value gets added to b. And so first we store the value of c into d into a register called ax, and then we store the value of b into register bx, and then we add the value of these two registers and store it into another register. I hope the example was clear. Moving to the execution, how I have done it is, suppose if after evaluating an expression, I return a value called -1 which gets pushed onto the value stack. So on the value stack, if the top of the value stack is -1, that means there is already a value evaluated and it's stored in a register. Now the next expression which is to be evaluated, it is to be stored in another register, and then I have to add those two registers. So I'm using the value of the top value of the variable stack, and based on that I'm evaluating the whole expression and I'm writing into the .asm file. The next module takes you to the conversion of assembly language instruction to intermediate level instructions. Here basically the intermediate level instructions consist of two things: an intermediate table and a symbol table. Symbol table is used to store the variables, the variable name, the size of the variable. If it is an array, it could be 10, 20 or any size which you define, and the memory address of that variable. And again there is intermediate table. It has the serial number and then the opcode of the instruction and the number of parameters followed by the opcode. Let me show you the code. Here I am taking the ASM file as input and writing into a binary file called intermediate file.bin. So the read file function, it takes line by line each ASM instruction, and then it passes to the evaluate line function. Here if the instruction is data or constant, that means I have to store it into the symbol table. So it makes a call to store in symbol table. So in store in symbol table, before writing into the file, I am checking if that variable is already present or not. Through this function get symbol address. If it is already present, I don't alter it, I don't make an entry anymore. But if the variable is assigned a new value, I update the value in the file. I update the value of that variable in the file. And then next comes, if the instruction is anything other than data or constant, I call store in intermediate table. So in intermediate table, I store the instruction opcode along with the variables, be that be a register or a number or a value, a variable. So the opcode for the instructions is specified over here. Like for addition, the opcode is 3, for subtraction it's 4, and similarly for the rest of them. And registers have the opcode. There are 8 registers: AX, BX, so on till HX. So AX starts with 0, BX is 1, CX is 2. Similarly, I'm getting it through this function, the opcode, and I'm writing all of them into the intermediate file. Next comes the code execution. The code execution part is you have to read all the instructions from the intermediate table and execute them one by one. So I have a structure called variable counter, which stores the count of all the intermediate table entries and also symbol table entries. So I traverse till the count is less than intermediate table entries. So then accordingly I will read the instruction opcode. So if the instruction opcode is 1, that means I have to move the value from register to memory. Then I traverse register to memory. So the values of the opcode of register will be stored in array of 1, and the value in the register will be register index. Similarly, I do all the operations like add operation, multiply operation based on the instruction code. Now let me take you to the execution part. I'll display the execution. So now we have stored everything into the intermediate file and we have generated the .asm file. Let me select the option. First would be the convert C to ASM. So it shows it has converted C to ASM. Now you can see the ASM file is created over here. The code is this, and the ASM file generated for this is this, int A, and you can see the specific is data A. Int P of 5, it's data P of 5. Scanf A, read AX, move AX to A. I'm moving the value from register into the memory. And then D is equals to A plus B into 10, B into C divided by 10. So first it takes the value of B and C into the register and then multiplies them, and then it takes into CX and then divides them, and then adds the whole value to BX. So this is how the ASM code is generated. I think it's clear. It follows the precedent order too. First B and C are multiplied, stored into AX, and then AX is divided with CX and the value is again stored in AX, and then add AX comma PX. I think it's clear. The next thing would be convert ASM to intermediate. So intermediate file is created as it is the first call to the program, and we have all the table entries into the intermediate file. Now if you notice, now I'm going to execute the program. 3. See, as there is scanf A, it is asking to enter a value. This will be the value of A. Let it be 10. And again there is scanf B. So I have to enter the value for B, that is 20. Now it evaluates the expression over here and prints the value of D. So 10 plus 20 into C. The value of C is 10 by 10. So 20 into 10 would be 200. First this gets evaluated and then that gets divided by 10. Twenty into 10 is 200 divided by 10. The value would be 20. And then it gets added with 10. So the result is 30. I hope you understood this. So this is how I executed my compiler program. I hope it was clear enough. Thank you. Stay updated for another videos on few more topics.